Good morning, all. We'll start around 8 o'clock, okay? And I think today I decide not to play some cheesy music, in the background while waiting. I'll tell you a little later. So I'm gonna go grab some tea and be right back. All right, I think that gets start, guys. Um, I think we'll start off as usual. Some friendly reminder. Today is April 30th, which is Thursday. We have a few items that I like to remind you, but also I have additional information that the president had, Dr. Guy has sent out. Some of you guys probably have seen it, but if you guys don't see it, I'll show you. Okay. Yesterday we have faculty meeting and we discussed, our teaching, any issue that we encounter, in the class and all those. Okay. Dr. Turner has mentioned about this, the financial aid that the state has allocated to Louisiana Tech. So I'll talk a little bit later on. Let's get started with our upcoming due date. Okay. Um, this weekend I decide to resume the quiz because I think the quiz it will help validate whether you guys follow me in terms of the class material, which I think that I have covered so far. I think I've been carefully select, and I believe that I think it will be important for you in your future career. It may not be direct immediately, but then somehow some of those concepts I think you need to understand. So the quiz I will post it tomorrow. I think you guys can start right after the dining philosopher done by Friday midnight. And then weekend you just review the material, and the quiz is going to be similar to what you guys have seen in the past. It's not going to be that difficult. Mostly you're going to ask some questions, so it will help kind of confirm your understanding for whatever the chapter that or the lecture that we covered so far, and also for someone who has not has or who has other commitment and didn't follow up closely, then I think that would help you to manage your time and then get on listening to our YouTube class and also do the quiz so that you will understand the material. Okay, so the quiz that we're gonna cover, I think it will continue on from the previous quiz. I think the last quiz we have asked you something related to process, but we also continue on talking about interprocess communication, which the short name or the acronym is IPC. Also, I think after that we also touch upon lightweight process, which is thread, okay, or multi-thread programming. And we also talk about the P-thread, which is the API or programming application programming interface that I think right now you are writing the assignment or your programming in dining philosophers, okay, which I gonna talk about the due date, which we postponed to this Friday midnight. The quiz also will cover the lecture 6 on synchronization and lecture 7 on deadlock, as well as today I plan to complete memory management, okay? I think after that we're gonna continue on into file management and see what happened, okay? But I think look into the material. I think I already decide the presentation schedule that I'm gonna talk in the next two bullet list. Okay, so if you guys have any question, feel free to put in this live chat, and I'll read and answer you as soon as I can. Okay, so the first friendly reminder, the quiz would be this weekend, and the due date is by Sunday midnight. Okay, try to be on time. I'm trying to be, work with you, be a little flexible, but I think manage your time well, so that you're not gonna pile up a lot of stuff that if you postponing, then you have another class activities, and then your time gonna get be compressed. Okay, the next friendly reminder item is the dining philosopher programming assignment. Okay, I have seen someone already submit your assignment before the deadline, and the new deadline from last time we discussed and unanimously you all want me to postpone. So the drop date, the deadline would be midnight by Friday. Okay, for someone who has not get start, you should start soon. Okay, it's not that difficult, but also I think it's allow you to put some thought and then write this program in order to understand the concept of multi-threading or parallel computing, okay? And also, I think this assignment, we would like you to kind of acquire the knowledge and experience in terms of communication, synchronization, as well as deadlock avoidance, okay? So I think my suggestion, I mean, to avoid the deadlock, because once you start using synchronization like mutex lock and unlock, I would say for my suggestion, treat all those chopsticks, okay, that would be on the left and the right would be the mutex variable. And then I think each philosopher try to grab the left and the right chopstick. But I think my suggestion, in order to avoid the deadlock, you can use asymmetric solution where you can treat uh, each philosopher passing the number or the ID of philosopher and determine whether that philosopher is odd or even number or index. Okay, and then if you identify is odd number or even number, then you pick the opposite side. Okay, first let's say that if it even number, okay, or odd number, then you may pick the right first and then the left. Whereas if it even number, then you do opposite. Pick the left first and then the right. Okay. So this would help alleviate the deadlock. Okay. So essentially, I have given you a sample code, okay, which is like similar to the example pt4.c, but I think I also add more variable that you can use in this assignment, which has some chopstick, okay. I think you need to focus on a few things, okay. First, I think in the function called I forgot what was the function that you pass to pthread underscore create, okay. In that you can implement the philosopher logic, okay, where the each once you are inside the that function, then you have to do typecasting, okay, because you're gonna pass a parameter which is the index or the ID of philosopher, and then after that then typecast back to integer and determine whether this integer odd or even number. And then once it's odd number, do what I suggest. The detailed descriptions already on Moodle on the PowerPoint that I walk you through this assignment. All right. So let's continue on to the next item, which is a lot of you guys have asked me question in terms of the presentation schedule, your presentation schedule. I probably cannot say exactly whether, for example, Carrick would do on Thursday or Tuesday. But what I'll do is I gonna start create a list or order list, okay? That I gonna say this is number one is this person gonna present this, this number two, number three, number four, number five, because each presentation, even though I give you a ballpark 10-15 minutes plus minus, okay, but sometimes some of you guys may have a little shorter, some of you guys may have a little longer presentation. So in that case, I think it would be difficult to say that, okay, John would do on Thursday, next Thursday, and then Carrick would do the Tuesday later on. I think somehow I don't want you to kind of get confused because you're being told to do on certain date, okay. So what I would suggest, you get ready by not next Thursday, so you have 1 week from now. The reason why I would start the first presentation next Thursday, because look into my material, I need to complete this chapter, which is memory management, okay. And then I'm gonna continue on to file management, which is one of the main large chapter, okay. Normally when I have time, I would also cover virtualization, okay, which if some of you guys will take distributed and cloud computing, when I taught that class many years ago, I cover virtualization there. I don't know the current instructor he'll cover or not, but I assume that it will cover in that class. But if we have time, I will cover virtualization. But the thing that I want to also talk about or go through is something that may help you in the last programming assignment, which is texture. Okay, so I will talk about, maybe I'll go through the main concept and show you some program, because some of you guys have interact with me, ask some help in terms of provide some sample code, which I did. But that sample code only work at certain aspect, not even complete whatever the previous assignment that I have asked my student in 222, but at least it will handle reading the input, tokenize it, and then handle three built-in command, which is cd, pwd, and exit. But I think this assignment that I want you to extend from 222, whoever took with me or who have not taken with me, then you're gonna do the whole thing. So therefore, I give you some starting code or whatever the sample code that help you to do built-in command. Okay, then you have to handle non-built-in command. For someone who has taken 222 with me, you probably have done built-in and non-built-in command, and also greater than sign, less than sign, which is redirection. This assignment, you're gonna add two more built-in command, which is list, okay, and set, okay, or you can define your own user variable, and then you can start building the symbol table that maintain those variable, because subsequent lines or later command, when after you define variable, you can refer to those variable, and that variable should be replaced by the value that you assign. So those are new feature that you're gonna do in this assignment. And then beside that, you should also support the pipe command, where there is a pipe vertical bar, and then you can connect two command, which is two processes. Okay, so in that, I think I will cover how to use, how to program the pipe using. There are a few system call that you can use to implement pipe. One of which you can use DUP and DUP2. So in that case, next class, which is next Tuesday, once I complete file management, I will cover some material that would help you assist you to do textual programming. Okay, does it make sense? So these are three major reminder that I would like you to kind of be aware of. Okay, the first one is the quiz coming this weekend, and then the second one is the dining philosopher program, which is the due date is this Friday midnight. And last but not least, the very first presentation. I think you all have to get ready by next Thursday. Okay, and then this coming Tuesday, I will give you a list of order of presentation slot. Okay, then you're gonna see which slot number 1, 2, 3. I'm gonna start sequencing, starting the first one next Thursday. Okay, so I think I told you the main reason that I need to have more time in order to cover some important class material. Okay, all right, so any question, please feel free to type. Okay, all right, the next one, any of us, because I have communicated to some of us, or some of us would like to talk to me on the Zoom, and then we try to set up time, and somehow I learned that some of you guys work full time somewhere. Okay, and that's what I bring. I never mention name. Okay, I bring some concern to the faculty meeting, and therefore Dr. Turner, who is my boss, he mentioned that Dr. Guy has sent out the information uh, yesterday, okay, regarding some financial aid. This is not the top whatever scholarship and all those, okay. There is another whatever the funding or some sort of funding assistance that state had provided, okay, which, let me just go to the next slide, is called CARES, okay, Corona AIDS Relief Economic Security Acts, okay. Some of you guys may already seen this, but some of you guys who has not seen, and if you have some financial hardship, okay, during this period, there are certain amount of money, I believe, a million or maybe $1 or $2 million that the state has given to Louisiana Tech. Okay, that if you can prove, I have no idea in terms of qualification, but if you guys have any issue regarding whatever the financial aspect, okay, then you can send email to cares grant at latech.edu, or you can go to financial aid website and get some detail. Okay, because the deadline, the application is May 15th. So this is just some information that, I mean, if some of you guys have some issue in terms of financial aspect, feel free to contact. Has nothing to do with the class, but I think we all cared about you. Okay, that's why, I mean, I like to share this information. I mean, if you don't need it, that's fine. Okay, we'll get through this period soon. All right, so let's continue on our discussion in the class, which is memory management. Let's do a quick recap. Okay, last class we start our memory management lecture and talk about, how operating system create a footprint of memory, process memory. Okay, we call process in memory, which is gonna hold your program or executable as well as the data. Okay, and then, your program may have function call that it will be managed by the stack that would be portion of this process in memory. Also, the heap is will be used for a dynamically allocate memory when, if let's say that you don't pre-declare or declare any variable, but then once you start your program, some logic is driven, whatever the program to acquire additional memory or create a new object on the fly. Okay, so therefore the heap will be used to dynamically allocate memory. As I mentioned, data is managed uh, or it's a storage for your global variables. Okay, and text is for your executable code. All right, and this is one given process. However, operating system, in most modern operating system will support multitasking. So in that case, you would have multiple processes running. So therefore, in memory kind of whatever layout, you're gonna see a bunch of process in memory or a chunk of memory that represent a given process. Okay, but then the process come and go, because when you execute some application and when you no longer use it, then you exit or terminate or kill it, right? So in that case, process come and go. So therefore, a chunk or segment of memory is being used or free, used or free. Okay, so in that case, we will talk about these memory allocation techniques. Okay, which we call, I think, two techniques that we will cover in this class extensively. The first one called contiguous allocation, and then the second one called paging. Okay, but then before we discuss or recap on contiguous allocation that we discussed last time, we also talk about the concept of address binding, meaning that every instruction, every variable, you would have address associated with all those instruction or variable or your data. Okay, but then those address, which is the pointer to the location of or the storage of your data or your executable or instruction in the memory. Okay, it can be created during compile time. That address will be generated during compile time or during load time or during runtime. Okay, if you recall compile time, when you compile your program, for example, GCC and then the file name. Okay, during which your program gets checked against syntax, whether all syntactically correct, and then continue on to check semantic before it create an object code. Okay, then, once you have object code, you have the code that represent your program, but sometimes your program may link with external functions such as printf, which is a standard library or standard IO. Okay, so you don't write your own printf, Therefore, you have to link from the library. So during load time, those address that associate with your variable can be delayed instead of generate at compile time. It may generate during load time and then link with this library function. Okay, but then those are some techniques that being used in the past, however in the current time or modern time. Okay, a lot of your program may be swapped in and out, okay, from main memory to secondary storage because of the virtual memory concept that would give an illusion of, if, even though you don't have enough main memory, then it managed by moving in and out the data, your process, your portion of your process memory from the main memory going to secondary storage such as SSD or the hard drive. Okay, and then when some of those memory or address being referred to, then it's gonna bring it will be brought back into main memory again from secondary storage. Okay, so therefore the address binding at runtime is important because every time when you program in memory, okay, maybe 20 milliseconds later on or 1 minute later on, it may not be in the same physical address or physical memory. Okay, so therefore you have to understand the concept of logical versus physical address. Okay, where the logical address is an address that associate with your program. Okay, that is a relative address. Okay, an address that the program or the compiler may generate, that your the lowest address which is relative to the whole physical memory start from zero, okay, up to the max number. But then when it starts mapping to the physical memory, then there is an offset register that you have to offset, and then from the, let's say the memory the address zero, maybe the physical address maybe 14,000 or something. Okay, because you're mapping from this relative address into the physical address. So the logical or relative address, okay, is a virtual address. Okay, which that it also give a benefit of how to move in or move around the process. Doesn't have to be in the same address all the time. Okay, so that's what we talked last time, and then we continue before we stop last class. We have complete the discussion on the first memory allocation technique called contiguous allocation. The contiguous allocation is a technique that operating system will allocate contiguous memory or sequence of memory is all consecutive, okay, all contiguous, okay, for the whole process. Okay, um, why it do so? Because in the past it does not require a lot of sophistication in terms of multitasking. You may have just like a handful of program running on your system. Okay, unlike nowadays. I think one time, I'm not sure this class, but in my 222, I have shown you my MacBook here. Um, when I do tops, okay, it's showing that I have 400 something processes running. Okay, so contiguous allocation is very simple technique, very low overhead, okay, in order to manage and allocate the memory. But however, it will not powerful enough that it can create or manage many tasks all at the same time. Okay, um, one I think the main theme is as I mentioned, it will allocate contiguous space. Okay, so therefore the technique has to maintain which portion has been allocated. So we call allocate segment, and also there it also should maintain a free segment, or we call whole. Okay, so in that case, once the new process coming, then the contiguous allocation will apply one of these techniques looking for holes. Okay, because you may have holes or list of holes scattered for the whole entire memory bank. Okay, now to find the hole that you can place the new process in those. Okay, you can either use the first fit or the best fit or the worst fit algorithm. Okay, last time when we talk about the first phase, okay, let's say that you have list of hole that available. Each hole may have different size, okay. The first phase is you are searching for the available holes, okay, or the hole that uh, first fit to the need of create this process, okay. Let's say if your process require 200 kilobytes, okay, the first hole you may have 58, the second hole you have 12, okay, so therefore 212 is the first hole that fit, okay. Therefore this is the algorithm, that one of the algorithm for contiguous allocation. So essentially contiguous allocation is a technique that you maintain whether which portion of the memory has been used, which are the free one, and the free one is just list of whole, okay. The second technique in, or the alternative technique in this contiguous allocation, called best fit, where the best fit is looking for which one is has least leftover memory. So in that case, the algorithm has to search the entire list of holes, okay, and then find which one is the best fit, okay. And then last but not least is the worst fit, that is looking for the hole that provide the largest leftovers, okay. So in this case, maybe it hope that the larger hole can be allocated, and then you can keep allocate on the larger hole, so that then in that case you may have more hole to allocate for incoming or the new process, okay. But then last time we worked on some sample, and then we demonstrate or showing the best fit, it's perform best, okay. All these holes, once we have leftover holes, and then sometimes even though if we combine all these holes, okay, we have large enough memory that may fit the new coming process. However, each hole or individual hole may not be large enough to fit for the new process. So therefore, those problem or those issue where we have holes but they aren't useful, okay, because they are just smaller than the new process, okay. It's called external fragmentation, okay, which is the leftover holes that even though the combine of them, the space is large enough, but then each individual is no longer useful. So therefore we need some technique called compaction or defragmentation, okay, that we can combine all these whole, okay. So I think and also we touch upon the internal fragmentation, okay, which is normally we cannot recover internal fragmentation, because internal fragmentation is the leftover of the last hole for the paging allocation that we're going to talk about in the next subject, okay. So I think this is what we end up last time. You have any question, feel free to type. All right, guys, so let me move on and discuss the idea of paging techniques, okay. The paging techniques, this is what we end last time, is a technique instead of we allocate the contiguous memory for given process. We divide the memory into an equal size, a smaller block, okay, of equal size called page, okay, at which each page size will be equal to frame size, okay. When we refer to page is a block of memory that we associate with the logical address, whereas frame is a the same size or the fixed size of block that divide on the physical memory, okay. So in that case, let's say that if you have the block size is 8K, okay, like 8K, because the block size could be normally power up to, it could be half K, 512 byte, all the way to 8K or 16K even, okay. Now, if you need to figure out how many pages that your system can hold whatever the entire memory is, okay, then you can, let's say that if you have 16 gigabyte memory, if one page is 8K, then you divide 16 gigabyte by 8K, okay, and then you're gonna get the number of pages in your system. All right, so in this case, when you allocate the process, okay, then it's gonna be a set of these pages that you string them together to represent one given process, okay, by using page table, okay. In that case, you have to track all the allocate page as well as tracking all free frame, so that the new coming process coming in, then you will get you will allocate, you know, the free frame to those process, okay. In order to run the program with size n pages, okay, then you need n free frame, okay, in order to load the program into those things. So that's why I'm saying that, you know, the concept of page and frame, where the page is represent your application, and frame is a physical memory that you divide those blocks, you know, in the entire memory bank, and then you're gonna get those many frames there. Okay, as I mentioned to you, the mechanism that you will create and manage given process memory is page table. So in that case, you would have a page table that you list page 0, page 1, 2, 3, 4, 5, all the way to the last page, okay, that would represent your process memory, okay. And in that case, the total number of the byte or pages is summation of all pages that represent given process. However, a lot of time, you know, the very last page, you may not use the entire page because of, you know, I mean, when you write your program may not be precisely, you know, the size as power up to. So therefore, the last page, you may have some leftover space that you don't use. I think it's called internal fragmentation, which normally you can't do anything, okay. So therefore, the size, the page size also dictate, you know, how much whatever the leftover or how large the internal fragmentation will occur. All right, guys. So I think this is some idea, and now let's the key thing how to manage whatever this paging allocation, okay, is based upon the page table. Now the page table, you have to translate from logical address, which is from this page ID to frame ID. So therefore, you know, given page table, you would have two aspects, or the address would consist of two type of information, okay. The first information is page ID or page number, which used as an index into the page table, which it will point to which physical frame or which frame ID, okay. And then within that frame or within that page, okay, then if you want to access variable I that define in whatever the address 16th within that block or that frame, okay, then you use page offset, okay, combined with page ID in order to define exactly which physical address that point to the memory unit or the variable that you're looking for, okay. So I mean, for example, if this is the entire addressing scheme, here you have page ID define point to which page, it point to page table, and then from your page table, okay, then you have a frame ID. This is frame, okay, which is then it would point to this is your physical memory, and then this is frame, for example, frame L here, okay. But then this frame L, maybe the block size is 8K, so the offset here, okay, you would use to point to exactly starting from the 0 of L and point to this D. So in this case, maybe you have your variable I here defined here, okay. So this is some idea how the address translation scheme work, okay, which will be used together with page table. All right, so I think this is more schematic showing, but this is more information beside, you know, page table. It also have a spatial field here, which I'm gonna touch upon later on. So essentially, this diagram show the address translation architecture, where your CPU or your program refer to certain address, okay, and that address consists of P, which is page ID, and then page ID would point to the frame ID here, and then after frame ID, let's say this frame ID start, this is the starting address of this frame F, and then offset with D here. So in this case, you can start access that particular address or particular whatever object or variable that you are looking for. Okay. Just quickly to touch upon this yellow field. This yellow field is called valid and invalid bit. Okay. Don't worry. I think a few next slides. Okay, we will have this valid and invalid bit defined. This valid and invalid bit. Okay, quickly is an indicator suggesting that if it's valid, that means that frame would be in main physical memory there. Okay. However, if that field is defined as I, that means either is not in main memory, okay, which it may be in secondary storage. Okay. So in this case, the concept of virtual memory, once you don't have enough memory, there are some portion of physical memory, okay, will be moved out so that it will free up that memory segment, and then it can bring in the memory segment that previously was in secondary storage, but then right now another program refer to it. So therefore it has to free up some space and bring it back. Okay, so the I may suggest that that frame or that portion of memory may not be in main memory, but maybe in secondary storage. But second case, okay, in case that you refer to non-exist, if that frame is invalid at all, so in that case, the operating system should trap as an error and report to user of that application that that invalid memory access. Okay, sometimes you might see a problem called segmentation fault, okay, or core dump that may create by invalid memory access. So I could have two meaning. One meaning is that that physical frame may not be in main memory but in secondary storage. And second meaning is that that I or that entry is invalid, that illegal access. Okay, so therefore the operating system should trap and report an errors there. Does it make sense? I think this is the main idea or concept that you have to kind of, grab on it and then continue on. All right. So now, as I mentioned to you, another aspect beside the address translation scheme and also the page table, okay, operating system must maintain a free frame list, okay, which is whenever you have a new process coming, okay, then it's gonna go grab the those memory or bunch of blocks, okay, which is bunch of frame, okay, so that it will allocate to the new process. Okay, so in that case, let's say that if you have free frame number 14, 13, 18, 20 and 15, okay, and then the number you can sort it or you can just come with this random, because sometimes the process free the memory, sometimes the process is moved out of the main memory and put in secondary storage. Okay, then the free frame would make some of those frame available and then put in this free frame. So now you have a new coming process that, for example, require 4 pages, 0, 1, 2 and 3. Okay, then you're gonna come into this free frame list and then pick the available one. Maybe your algorithm would say that, okay, just pick from whatever that order that provide in the list. Okay, so that you don't have to add additional overhead in order to sort this list. So in that case, you can just assign 14 to page 0, 13 to page 1, 18 to page 2, and then 20 to page 3. So therefore, you create a new process page table and then populate the frame, the free frame, okay, and then mark those frames are unavailable, remove those frames out of the free memory. Now you get the new page table. So every process, okay, you would have page table. That's one implementation, a simple implementation, that each process would have its own page table. But there are some shared page table that you have to use process ID in order to combine many process page table into one table. We'll talk about this little later on. I think that technique called inverted page table. Okay, but then this is just one idea how the new process get allocate memory because as I told you, in terms of paging memory allocation, the operating system will assign a set of free frame, okay, to consist or to make up a given process. So in that case, frame and page are the same size, and therefore, given process is it require four pages. Therefore, you have to assign four frame or four free frames there. Does it make sense? All right, so let's move on. If you have any question, feel free to type here. Okay. Now, quick idea on how to implement page table. Okay, normally page table is always kept in main memory. I think that suggests that you should not operating system should not move page table into secondary storage. Why? Because I think it's important or main piece of information or tools in order to map logical address to physical address. Okay, so if the page table is moved to secondary storage or not in main memory, and therefore there's gonna be way too much overhead in order to bring it back, and the mechanism how to refer to the memory is just kind of incomplete. Okay, so therefore page table is always or must be kept in main memory. Okay, then within this page table implementation, okay, then you would have two type of register. The first register is page table based register. Point to the page table, and then you have page table length register is the indicate the size of page table. Okay, in some scheme, sometimes the data access require every time when you would like to access have any memory access. Okay, for example, when you say a equal to b plus c, okay, every time when you refer to b a b c, okay, that means you have memory access, you refer to variable a b and c before you start doing operation. So therefore you have to look up to this page table and then see the index there, and then from that index it will point to which frame, and then that frame you have an offset. Okay, so at least there would be two memory access, okay, in order to bring the data into register and start perform some operation. Okay, so therefore in order to improve the speed of this memory access, okay, there are some implementation of page table that include the concept of cache. Okay, but this cache is not cache on the CPU. I think the techniques called associative memory, or another term, technical term called translation look aside buffer. Okay, which is essentially is a page table cache. Is a very fast memory, and then the way to look up for each page table or page ID, it would be much faster than look into the memory. Okay, so I think let me show the diagram and you're gonna see it clearer. Okay, so normally when you want to do any memory access, okay, first whatever that address has to look up into this page table, and remember page table normally in main memory, so you have one memory access. Okay, and then after that, okay, then after you have frame ID, then you offset to the D, which is the particular address within that frame. Okay, so therefore you have to do this operation and then do the second access. Okay, this operation you may perform in register level, so the overhead may be small, but then this is another memory instruction that you have to read. So minimum you would have two memory access plus a little more overhead in order to perform this lookup and also this offset calculation. Okay, and therefore if your application is memory intensive, uh, every time when you do memory access, it requires two memory instruction. Can we improve this memory access 20% or 50%? Okay, this is the attempt that associative memory, which we call page table cache. Okay, which it has ability to do parallel search. Okay, so it quickly can search for, this is a special hardware or memory that perform the mapping between page ID and frame ID. Okay, and then some of these operation can be done in parallel kind of parallel computing. Okay, so in this case, instead of one memory access overhead, the overhead of this associate memory or parallel search, it may be 1/10 of an overall performance, okay, with respect to the memory access. Okay, so let's take a look at the next diagram, and then you see how this thing works. Okay, so last time we don't have this one. Every time when we want to look up, give an address from logical address, we're gonna go to the page table. Okay, and then so the page table is stored in main memory. So in that case, we have one memory access, and then this is the second memory access. We have additional kind of overhead where you need to perform the offset. Okay, now to improve the speed, to speed up this memory access instead of two memory access. Okay, then we can catch, if we know that certain frame would be frequently used. Okay, then we will store those frame. Okay, like frame 10, frame whatever, 50, certain frame. Okay, into this TLB or associative memory. Remember I mentioned in the previous slide, TLB or um, TLB translation look aside buffer. Okay, which is another term called associative memory. If you guys know Dr. Ben Choi, okay, his PhD is in this associative memory. I know him quite well because we work together almost 30 years or 25 years. Okay, I used to work for AT&T, graduate 1994, and I think Ben graduated from Ohio State around close to 2000, and he joined the team. So we work in the same team, and I interviewed him and asked him what was his dissertation. He said associative memory, and since I know this operating system quite well and know page table, so we have good conversation there. But anyhow, the idea in which you are catching this, I mean, it look big, but in fact it's a small portion of memory when we compare to this page table. So let's say that if page table you have 150 entry, maybe perhaps like 20 entry you can store here. Okay, and normally you would the compiler, part of compiler would know that which variable or which page has been frequently used. Then you would catch some of these table or this entry into this TLB, because the TLB may be 10 times faster than regular memory access, because it uses spatial memory and it has parallel search capability so that it can search quickly. However, the size of this is much smaller than this, so therefore you must store only the important page that it will be frequently kind of access. Because when you have your application, sometimes certain variable you declare but you never use it, but some variable that you use it so often. For example, if your program has iteration or loop, okay, then obviously if you have index I, that I from I equal to 0, I less than n, and then I plus plus, and then if you say n is a million times, so therefore I would be accessed million times there. And so that I would be a good candidate, that if I reside on certain frame, okay, then I would, if I have the intelligent runtime, the runtime should catch those page or the frame that has I variable into this TLB, so that it will reduce, instead of 2 instruction, it may be 1.5. Okay, let's say that if TLB is 50% faster, therefore you have speed, the speed improvement 50%. Does it make sense? But again, this is the idea of cache. Okay, we call page table cache. So it's not guaranteed that all the time you're gonna have a cache hit, or we call TLB hit. TLB hit meaning that whenever we look for a certain page, okay, that page would be in this TLB. So that means we say that TLB hit. But then what if it's not there? then we have to go all the way to regular page table, which we know for sure that it's going to be there if that valid page. Okay, so in that case, when the TLB miss, then you can have to go to the regular page table and look for that frame before you start do offset and then point to certain address. Okay, so this is the idea showing how to get a performance improvement in terms of memory access, okay, by introducing a page table cache using TLB or the whatever hardware technology called associative memory or translation look ahead buffer, okay, which is a fast buffer that you can store page table or portion of page table there. Make sense, guy? All right, so let's move on. I think that TLB, as I mentioned, is associate memory. You want to know more? Dr. Choi, when the whatever the we end of this coronavirus or this COVID, then you can go and talk to Dr. Choi, pick his brain, ask him that Dr. Choi, I want to know more about associate memory. Can you tell me more? Okay. All right. Now, as I told you in the past, okay, I don't want you to remember everything, but I want you to understand the concept, and in a way that you can start think about those concept, okay, and then apply. Let's say that if you're looking for speed up your application, and your application when you start look into more detail, that is memory intensive, okay. And in that case, let's say that you're gonna choose the hardware. One set of hardware may have whatever this speed up or memory access using TLB. Another one may not have, but then the one that have this TLB may cost maybe $50,000 more, okay, versus another one is $50,000 less, okay. But now, let's say that if you want to calculate to see whether investing more $50,000 more is worth it or not, okay, then if every time when you perform certain operation, you can equate that operation to dollars or to money or to income or to revenue that you make, okay. So in that case, perhaps if you want to calculate and understand what is the effective memory access time, okay, with respect to this associate memory or associative lookup, okay, then we can define, let's say that if whatever this epsilon associative lookup in TLB cost epsilon unit time, okay, assuming that if the memory access time, regular memory access time costs 1 millisecond, okay, and then alpha define a hit and miss ratio or probability of seeing that page ID or page number in the page in the TLB. If it's not seen in the TLB, then it has to be in the page table. Okay, so therefore you can define the effective access time. Okay, which is 1 plus an epsilon multiplied by alpha. How do we get this 1 plus epsilon? Because in this case, if we go back to here, to access, if that page is in this TLB, it's gonna cost this epsilon, okay, or sigma, whatever you want to call, okay. Um, and then so this is one cost, okay, and then you have another cost by offset, and then access the physical memory is 1, okay. But then the probability of hit is alpha, okay. So therefore these routes, when you go and access here, it's gonna cost 1 plus this epsilon multiplied by alpha, okay. But what if it missed, what if you don't find the page number here, then you have to come down here. So that means it have to hit one mouth, it try to access here, which is 1 epsilon. If it cannot find, then it go down here. So this is epsilon 1 and 1 here, right? So therefore you're gonna have alpha minus 1, okay, which is probability that miss, meaning that you go this route. this route, okay, is TLB miss, okay. Then multiply by 1 plus 1 plus epsilon, okay. So therefore you're gonna have 2 plus epsilon multiplied by 1 minus alpha, okay. Does it make sense? I don't want you to remember this result, but I want you to be able to analyze and then come up with those notation, okay, because you can simplify whatever this expression, okay, or cost function that based upon physical problem, okay, and then end up to derive this, okay. Because why? I think last OS class I asked similar question in the exam, okay, but I slightly change some attribute there, and then the student, I think they study hard, but he didn't understand, so he remember whatever the last simplified result here, and then he just copied this. So in that case, I can't give him any score or partial score, because I mean my point is I want you to derive from, I mean, this physical problem, and then come up with step by step to show how you understand and then do analysis. Because in near future, let's say that when you start working for industry, you are a technical lead that decide to acquire certain hardware, and then you understand, or the vendor may present you with certain architecture, but he or she may not present everything, because the vendor may not understand how your application or whatever your service that you can deploy on this hardware. So you are the one who know, you are the one who will be able to tell whether this is memory intensive or database intensive or IO intensive or whatnot, okay. But therefore you gather certain type of information, okay, and then if you have ability to do analysis, okay, and model, and then come up with the result or all this, because I mean this alpha or this epsilon gonna change, because if you buy different model of the hardware, okay, or you buy larger size of this TLB, the alpha gonna change significantly, because the larger the cache or the page cache, okay, and therefore the larger the alpha is, because the larger meaning the higher probability that it gonna hit rather than miss, okay. Make sense? So I think, guy, this is really important to you, even though I mean it's related to operating system, but the concept, the idea would help you to be the better architect, the better system designer, okay. Don't try to compete, I mean say that, oh, I'm gonna be programmer for the rest of your life. I would say programming skill you will use as entry level when you start getting in, but then once you are into organization, you want to grow, you want to be the leader. So the programming skill is I would say the commodity. I mean perhaps a lot of that a lot of company outsourcing those programming to the country or the location that cheaper, but then they cannot take away the idea, they cannot take away our technical skill that would see an overall picture. We understand how to map our business using whatever technology in order to apply and make our company to be the world class, okay. So I think that's what I'm trying to emphasize to you, that don't remember this formula, but then know how to derive this formula, okay. If you guys I hope you guys follow me, because I think this is exactly I'm trying to show you. Because there's if you see this diagram, there's two, I mean at least there's two ways that to access a given address. One is when you start introduce TLB, which is supposedly to be a concept of page cache or page table cache. It speed up the whole thing, but then that page cache would have limit size of storage, so that you would be able to store portion of the page table. So normally you would find any variable that reside on certain page, then you're gonna cache that page or that frame into this TLB in a hope that you're gonna get some speed up. But in order to calculate whether what is the speed up, okay, or which of the model of the hardware you want to buy, because if you have 5 choices and then each choice has different size, like for example when you buy Intel processor, you heard about L1 and L2 cache. some of the high-end processor may have larger L1 and L2 cache versus the lower end. Okay, so in that case, the cost, the capability, you have to understand all those. Okay, why don't we do this, guy? Let's take 3 minute break. Okay, right now it's 9 o'clock. Okay, and by the way, I didn't mention to you, I think in before we start, I said that we're gonna start the class shortly. Also, I said that this time I'm not gonna play whatever those music that it does not, I don't think it sound good in the background. But last time some of you guys report to me that you guys can't access my video after, because it's automatically upload there. But then I play Pandora, which is innocently, yet I play all the time and it's legal. Okay, but then when I put in the background during the break, okay, somehow YouTube, when you upload it's also analyze the content and detect that there's some song that has some copyright, so therefore it's block that video. So I have to go and, hold the whole 9 yard, try to trim that thing out, try to kind of rectify the problem. Okay, so so in that case I decide, just quietly take a break. And so I'll be back right now. It's 9:01. Be back around 9:05. Okay, 9:04, 9:05. Okay, all right, guys. So quick break. I'm gonna go grab some drink and then kind of clear up my throat. You guys have any question, feel free to type. You guys don't follow, okay? Because some of this idea, I think it's quite important, okay, in order for your future. Because part of your application, memory also is important component in order for you to make your application work or work well. All right, guys. think let's continue on. Thanks, Bryce, for your compliment. Memory protection, okay. I show you on the previous slide regarding the page table. And if you notice that the field that I highlight, the yellow field, which we call valid and invalid bits, okay. Those are an entry that used to manage whatever each page table define whether that page is valid, meaning that it's already being deallocated, or that page is not in main memory. Okay, so the valid and invalid bit, okay, is implementation that trying to indicate whether when it's valid, that means associate page is in the process logical address is legal, and also in the main memory. Okay, however, if it indicate invalid, okay, that means it indicates that the page is not in the process logical address space, whether it's not in the main memory, real main memory, which but it also can be in the secondary storage. So what I'm trying to say is that if it's valid, then you know for sure that you can use it right away. If it's invalid, then operating system need to handle. Okay, by first will look up into the page list whether it's in secondary storage. If it's in secondary storage, then it should bring that page back into main memory. Otherwise, if it's not in the secondary storage, then it should declare that this is illegal memory address access. Okay, so I think this is the implementation that I show you. So beside page table that you have page ID associated with frame ID, you also have one bit field, whether it indicate 1 or 0, 1 meaning valid, which is that page is made in main memory. If it invalid, okay, then there are two cases. All right, so let's take a look. If it valid, then there's no issue, then you just go and access that frame directly. Otherwise, if it invalid, okay, then well, I think um, the point that I'm trying to link to this idea is something associated with a swap in and out, which is in the past, the virtual memory, you swap the whole process out and process in, okay? But in the modern time or modern operating system, it only swap out portion of given process, because the page each process is broken down to be multiple pages that page table used to maintain all those memory based on those individual page. Okay, so modern operating system, it would not swap the whole process out, because the whole process may be very large space, so therefore the page or certain page will be moved out. Okay, and normally how to move in and out, the decision have to make in by predicting that whether that page will not be used or will be used. Okay, so anyhow, so I think that lead to the virtual memory. Okay, which is a mechanism that provide an illusion to expand the memory view into secondary storage. Okay, because as you know that you may have hard drive which is many terabytes versus your main memory that you may have 1 gigabyte up to normally you have like 16. Sometimes you have high end, you can add up to 32, 64 gigabyte or 128. Okay, but normally the main memory it will be much smaller. So the virtual memory is mechanism to move certain page in and out between frame, and then the frame in between memory into the hard drive. We call, in fact, this virtual memory we call demand paging. Okay, which is move in and out the page on demand. Now the demand paging is allow the page to bring in page into the memory only when it needs. Okay, so in that case you don't have to move the whole process out and in, you just move only certain page in and out, so therefore it will promote and so that you have less IO need, less memory needed. Okay, and then faster response, you can support more user. Okay, now when the page is needed, okay, now going back when we want to connect this to the idea of valid and invalid bit. Okay, so in that case, if the field in which that associate with the certain page entry or page ID and frame ID that you have either valid or invalid. If it valid, then you have no issue. It's gonna be in memory. Therefore, you go ahead and access those. Okay. But then if it invalid, okay, then there will be two cases. Okay. The first case, if it is totally invalid reference, okay, then operating system should trap and then report an errors. Okay. Otherwise, okay, if it's not in main memory, then it bring those portion or those page back into the memory. Okay, so in this case, certain page would be swapped in and out in between secondary storage. Okay, now let me show you, I think this diagram we already show you some field is valid, some field is invalid. And then once it's invalid, maybe it's actually in illegal access, or maybe sometimes some of those entry is outside in the secondary storage there. Okay, so once invalid happen, then we call page fault. Okay, lot of time when you have invalid indicator, okay, it will trigger an event called page fault. Page fault. FAULT. Okay, which is an event that operating system will handle this page fault. Okay, and then once page fault happen, okay, then there will be 6 steps that operating system will handle. Okay, first, okay, the page fault it indicate, then operating system trap that event, page fault event. Okay, and then it will look up and see whether that page is in backing store or secondary storage. Okay, the term backing store also refer to your secondary storage or hard drive. If it's in secondary storage, okay, then bring that missing page back to free frame. Okay, what if you don't have free frame? Then you have to find a victim frame that you're gonna bring it out, okay, and maintain into the secondary storage, so that you will have free frame, and then that missing page will replace that free frame. Okay, and then after that, then you update I to be V again, because that page already restore back, and then from invalid it's gonna be valid back. Okay, otherwise if you can't find that missing frame here, then that means in illegal access, memory access, then you should terminate your program. Okay, this is important 6 step that how operating system handle page fault. Normally, when I have final exam, I'm gonna emphasize it and tell student that I might ask a question such as, what is the memory, what is the page fault event, okay, when it happened, and how operating system handle. Okay, the page fault is happen when it detect that that page entry, okay, it indicate invalid. So that means that is page fault event. So operating system will handle with these 6 steps in order to bring the missing page back into physical memory. Okay. Otherwise, if that invalid, it can't find the missing page. That means it's illegal memory access. So therefore, operating system will handle by terminate your application. All right. So that's an idea of the page fault. Okay, so as I already alluded to this, I think last time I said, what if you don't have free frame there? So what happened if there's no free frame available and you have missing pages that you want to bring back into main memory? So in that case, some operating system will have page replacement mechanism, okay, which it will responsible to find some pages in main memory, okay, but not in really use, and swap it out. Okay, there are a few algorithms that you can apply to this page replacement, but it also result in different performance, because what if you replace that page, okay, take that page from main memory, and then the next clock cycle you refer to that page again. So that means you're gonna keep move in and out from main memory and secondary storage. You know that the hard drive is like 1,000 times or 100 times slower than the main memory. Okay, so in that case, I mean, you can have performance hit very severely. Okay, so some page, as I mentioned, okay, may be brought into memory back and forth several times. How do we know that which task or the page won't be used for a while? How do we know that? sometimes the runtime operating system has to work with compiler, or maybe you can do profiling, instrument your program, look into the program and start predict how the usage, the pattern of how variable get used, okay, so that you make the operating system in terms of page scheduling or page replacement smarter. Some of you guys who work on the term paper on AI in operating system, I hope that you might have seen or come across some idea on AI into this page replacement or certain thing, because I believe that using machine learning, or these whatever the data, the pattern usage, okay, training operating system. I mean, right now you have system that sometimes is mission critical, so you have limited resource, but then if you have some system that you want to perform well, and you engineer enough whatever horsepower to the system, then you can add some AI in order to make those operating systems smarter, okay. So now let's take a look at slightly different page table structure, because so far we talk about just like one straight one level of page table, okay. However, page table can be much more sophisticated, okay, such as you may have a multiple layer of hierarchical paging, okay, which means instead of you can think about page table as an array of something. So it's just one dimensional array, right? But then you can think about if you have process that very large space. So therefore, if you have one page table, it can be very long. What if you want to optimize in terms of searching? Because sometimes when you want to look for something, if you break into hierarchical like tree, like, okay, then you can apply some algorithm that process on tree quicker. So therefore, there's some introduction of sophisticated or different structure of page table or paging, okay. So we're going to talk about hierarchical paging, and then touch upon hash page table using hash function, okay, together with page table in order to map between page ID or the address to physical address or the frame ID. And last but not least, we're going to touch upon inverted page table. So hierarchical page table, the idea is break up the logical address into a multiple page table or multiple level of page table. The simplest technique of a hierarchical page table is two level page table, okay. As such, you're gonna see example here. This is the regular addressing scheme, okay. Assuming that you have 32-bit machine, and then each of the page size is 4K. So in that case, you will divide, the page number consists of 20 bits, okay? And then the page offset is 12 bits. All right, guys. Now, since the page table is pages and the page number is further divided into 10 bit and 10 bit here, okay? That means we're going to divide into two levels, okay? The first level is P sub PI and P2, or PI and PJ, okay, which consists of 10 bit and 10 bit here. That means the total number of page entry at the first level, you're gonna have up to 2 over 10 or 2 power of 10, which is, I think you can calculate. But then each entry of the first level page table would point to the second level of uh, the second level of the second level of page table, okay, which you can use the second number to point to the entry, and then you get a target frame ID, and then you can do this offset, okay. So the next slide will show you how this thing works, okay. Here this is outer page table that you can use P1, okay, which is point to this, and then you can use P2 together with D, the offset, okay, point to particular entry point, okay. I think essentially instead of one level page table, you break up, the page one large page table into multiple level. In fact, you can have, if you can have two, you can have three, you can have four, you can have five. Okay, I think it's up to the system, the situation, which one would be best. But I think this is just one idea. Instead of one level page table, you can break them up into multiple level. We call hierarchical paging. Okay, so this is just one idea how to make page table more complex in order to address certain concern or certain issue. Okay, as I told you, if sometimes you have very large process, okay, one entry of page or one level of page table, then that the array could be very long, very large. And then when you have a level long, very large, the way the searching in order to get to certain entry, it may take more time than when you hop through two levels. Okay, so I think this is just an idea. Now, yeah, I think this is also more idea, more detail how I mean, to break up the whole page ID as large table into two level of table. So the first P1 would point to the outer page table, which give the entry, okay, that point to the second page, because here you may have different page. Let's say you have uh, n number here, n number entry, then therefore the second level you're gonna have n inner page table, and then you use P2 to point to that entry, and then you have the frame ID. Once you have frame ID, then you offset. Okay, so I think this is a scheme to demonstrate hierarchical paging, and then showing you only two level. Okay, but then you can do two level, you can do three level, four level, five level. You just break up all this address into smaller one. The whole thing, the total number of bit that you represent still the same. Okay, if you have 32 bit or 64 bit, then you have to divide certain portion to be the offset, and then the rest gonna be the kind of page ID mechanism, whether you're gonna break up into two level, or later on we're gonna use the same whatever this page information, and then include all the type of information as well. Carrick has asked, "Do you get my email about meeting you?" We'll talk about. Yeah, I think I'll check later on. I have not checked yet. Someone just sent me some question again, but I'll check the email later on, Carrick. Okay. Let's move on this. Okay. The next one is hash page table. If you all know hash function or hash table, then you can easily understand this. Okay, so this one, assuming that we have one level of page table, but instead of only page ID. Okay, meaning that if we have just the regular index, okay, which is an array of something, we can create a simple page table. However, instead of we just use those index, but we use hash function in order to find the entry point, so that we're gonna see the frame ID that this hash index point to. Okay, so normally, I mean, this is the idea of hash page table. Okay, the virtual page number is hashed into the page table, and then this page table contain a chain of element of hash function to the same location. So if you have good hash function, therefore the chain that this hash number point to should not be long. Okay, it should be spread out evenly there. That means suggests that good hash table should spread out, the index, where when you start passing the seed, the attribute to hash function, it should kind of generate the index that's spreading throughout the whole table. So the virtual page number then compare, if you have collision, okay, the virtual page number will compare in the chain of the search for the matching. If the match is found, then the corresponding frame ID is would be point to or use. Okay, so the idea is showing in this diagram. Okay, where P instead of page ID that map to the regular index from 0 to n minus 1. In this case, we use hash function. Okay, and then this hash function then we'll use to generate the index that would point to the frame ID. But then the same whatever this P or the page ID that using hash function, it may point to, even though different ID, it may point to the same entry point, and therefore if you know hash table, entry of hash table is the linked list of those data that you want to store. So in the case that if you have two pages that point to the same index by hash function, okay, then you have to perform the searching, okay, to find the matching one. All right. So I think the point is it's just another alternative solution instead of using an array of something and using index by mapping page sequential number of page ID from 0 to n minus 1. We can use hash function, okay, as a mechanism to point to the bucket or to the frame ID. Okay. Um, that's it, okay. And then after you find one, okay, then you use the offset and then access those address, okay. So this is the idea of hash page table. Now, last but not least, in terms of page table, we call inverted page table. Okay, in this case, you have one entry for each real page memory, meaning that you can combine all processes. Okay, normally each process would have its own page table, but then you can combine all processes, okay, into one page table. Now, but then that page table, you also have to have additional information such as process ID together with page ID. So in that case, you have two information together to represent a normal page ID for that given process. But in order to identify that page ID, because you may have page ID 1, which is belong to process 1 and then process 5, okay? And therefore, you have to be able to distinguish between page 1 that belong to process 1 or page 1 that belong to process 5, okay. So therefore you're gonna add uh, the information with respect to the specific to that process, okay. So therefore you use process ID. So in this case, entry consists of virtual address of the page stored in the real memory together with that process information. Simple process information could be PID or process ID. Using inverse page table, that means you consolidate. If you have normally when you have a normal page table implementation, if you have 100 processes, then you can have to have 100 page table. What if you just create one large table that you want to manage a page table for everyone or all the processes, and you can reuse, so then you don't have to create and destroy all the time, right? In that case, inverted page table would support this idea. So in that case, you use hash table in order to identify which process ID, okay, that page belong to, okay, and then you use page ID together with the process ID to map to particular frame that belong to this page, and this page belong to this process in order to find out the final address or physical address in the main memory, okay. um, Take a look at the diagram. I think you're gonna see this well. I think this is the concept that I'm trying to explain to you. So in this case, normally, we have the normal page table. You have page ID and then the offset, right? In this case, the whole addressing scheme, you include process ID too. So here in that case, you have this unified page table that can be used for any type of processing. Okay, so in that case, you have to have sophisticated way to search, quick search for PID, match PID, and then with the page ID, okay, and then it will point to the frame ID, and then you can use this to offset with the information and then find physical address, okay. Can combine with hash function. You can combine with some search algorithm in order to perform searching for the frame ID and then eventually find the target physical address there, okay. So the idea is not that hard, okay. All in all, it's just another solution in order to address different needs, because sometimes you may have limit memory. So therefore, instead of, or you may have a large overhead when you create a process, and then every time when you create process, if you use traditional page table, then you have to create page table as well. Okay, so then in that case you have two overhead. What if you have a unified page table, like inverted page table, that one large page table, and then that page table can be used for all the processes. However, you have to identify whether that page ID, okay, belong to that given process. So therefore, you just include a PID as an address, okay, scheme, in order to identify which of this address belong to which process. Okay, that's the main idea. You guys with me? So this is just three alternatives that beyond regular page table that we talk about. The first one is hierarchical paging. The second one is hash page table. And last but not least is inverted page table that include the process ID. Okay. All right. Okay. um all the memory management techniques, okay, I'm not gonna touch upon a whole lot, okay, because I think pretty much I'm pretty satisfied when I complete the discussion with the between two major memory allocation, which is contiguous allocation and paging. Okay, some early system using share pages, okay, or segmentation, okay, such as in Solaris, which is Sun Microsystem. Right now, I think there's no Sun Microsystem because Oracle bought Sun, and I'm not sure whether they continue selling the hardware or not because Oracle is mostly like the software company, okay. So therefore, some of these technique may no longer being applied or used, okay. So I think you can read and try to understand, what's out there, what is the historical aspect in terms of memory management. Okay, it's just for your information, FYI. Okay, I think we talk about these share pages and the idea of share pages, that instead of each individual um, process has its own page, some application it may share among many processes, so you have share pages. And then we have segmentation concept. Instead of you divide into equal size, then you just allocate section of memory to represent certain program, certain application. Okay, so let me just, I think the rest are certain memory management implementation for different systems. For example, the Intel 386. The reason why I'm quickly, I mean, go to this slide. I think these are optional. You should read. I think I would suggest you should read. But in terms of concept, I would end at the contiguous allocation when we end the discussion of the last three alternative page table implementation that include hierarchical paging, the hash page table, and then inverted page table. Okay, the share pages, segmentation, the implementation to certain hardware. I think you can read by yourself because 10 years from now, you may not have Linux or you may not have Intel 80x86, but those concepts in terms of allocation, those are abstraction that hardware agnostic. Okay, so therefore I'm still seeing that those gonna be used for a very long time. I don't see that any other technique will replace them soon. Okay, so otherwise, I think I will end the discussion on this memory management, and then I'm gonna continue on. If you guys have questions, feel free to type for me. I'm not sure I'm going too quick or not, but I'm hoping. I think someone said that my lecture or my YouTube is scrubbed. I'm not sure whether I'm dragging on or not, but I think all this is important, and especially we don't see face to face. I have some concern that because a lot of time when I teach in the class, I can have eye contact. I can feel whether you follow me or not. So therefore, sometimes I need to kind of recap, emphasize on something so that you're with me. All right. So feel free to type me some question. Otherwise, last 10-15 minutes. Okay. I want to go to the next lecture so that um, I'm plan to give you a major lecture up until next Tuesday, and then after that, the Thursday we're gonna start the term presentation. Okay. All right. Okay. So let's go to chapter 11, which is lecture 9. Okay. In the book edition 8. I just go back to my old book. In fact, I use since edition 2, not edition 3. Okay. You can tell how old I am, because each edition, it does not come out every year. I'm not sure the latest version of the OS book is edition 9 right now, maybe 10 or 11. Okay. But let's start on the file management or file system implementation. Okay. This is one of the important modules. Okay. In order to make your operating system complete. Okay. I mean, so far we talk about process concept, which has a slew of things that support process concept. In fact, chapter 1 all the way to chapter 7, we spend more than half of the course, because essentially, your application require operating system. I mean, to execute, and then your application will be execute in the form of process. So therefore, processing, okay, a process of processing is very important concept. And then beside that, the process can be executed. You have to have memory. So therefore, memory management is quite important. Okay. And then last but not least, you have data that sometimes you may want to store the data permanently, because normally when you shut off your system, the process gone, but your file, your application still reside in the file in your storage. Okay. So then when you restart the system again, then the operating system will kickstart your OS and get the environment ready, and then you can start execute your application. To execute your application, you have to load those application from a file. So therefore, file system is one of the most important aspect in the system that you use today. So therefore, is one of the last chapter, okay, which is chapter 11. I think I skipped chapter 9 and 10, because chapter 9, I believe, is virtual machine, which I already touched upon it, okay. It's not a whole lot. And then chapter 10 maybe device management, which is similar to file system implementation or file system file management. All right. Okay. Let me take a look. No question. Let me continue on. File system implementation. Okay. The outline of these chapters. Okay, will start with the file system structure and how it look like, and then we look into a few implementation of file system. Okay, and then when you have many files, then the directory come in play, because you need to be able to organize collection of files together into one folder or directory. Okay, and then we're gonna look into how the storage get allocated for file. So in fact, when you start thinking about a file, there are two aspects. One is a file header, or the information with respect to a file. And then when we talk about information, it's not the data. Those information or the file header point to the data that's stored somewhere. So that we will talk about the allocation method. Okay. And then after that, we will discuss about free space management, some overhead efficiency performance, the recovery, because sometimes when you shut down the system, if you open but not close the file, you may have stale file that need to be recovered. Also, we'll touch upon or look into the log structure file system, because anytime when you do something with files, okay, the system will log the activities, such as when you write something, or normally read. I mean, read is not destructive, but whenever you update or write something, you change those file information. And think about when you update something, right? You're writing for your CPU, your application running on CPU, and start flushing, okay, or write something into cache, and then from cache, maybe from cache on CPU or the memory, okay, or maybe you have a buffer cache, okay, somewhere. and now then it have not written into your storage, because your storage also plug into system bus. So you can see that for computing time, when you start saying that, when you start attempt to write something, when you open file and write, okay, then the whole data, if you shut down the system and then the writing operation is in between, that file gonna be in stale file, because file still open, and then maybe a few bytes have been written to that file but then not complete yet. You have not commit that operation yet, right? So therefore the log structure would help in order to recover a file, okay, to roll back or to provide, some recovery or suggestion that you need to do something. Last but not least, we're gonna touch upon network file system. A lot of you guys enjoy this network storage, cloud storage. Okay, I think those are evolution from network file system that growing. Okay, so network file system, in fact, is invented by Sun Microsystem. As I mentioned, Sun 20 something years ago used to be a top computer company in the world. It's just like HP or Dell today, but with things go by, times go by, big corporation is become dinosaur. The smaller, the high tech company, the disruptive technology kind of conquer the world. So if your company are not moving fast enough, you get eaten. Even though Sun has invented a lot of great stuff there, including NSF or network file system, Java also invented by Sun Microsystem. Um, so I think this is the outline that we talk in this class. Okay, and if we have time, we're gonna touch upon a cloud storage as well. Okay, how the file implementation, related to uh, cloud storage. Um, well, as I mentioned, the objective here is describe how the implementation of the local file system, the directory structure has been made, and the design, the justification, and then look into the remote file system like the network file system, discuss a few algorithm in terms of block allocation, free block, and the trade-off. Okay. Um, Now you have seen this diagram quite a while, okay, and as I want to highlight to you, you can see that these are a example of Linux kernel, okay, that you have kernel level here, okay, and then the kernel interface with the hardware level. In fact, if you zoom in into this Linux kernel, essentially there are two major aspects. Okay, on the right hand side, it's called process control system that include process management, scheduling, and memory management, inter-process communication, or IPC. And then on the right hand side, you have file system that include block device and character device. Okay, the block device mostly for secondary storage, hard drive. When you have device that it transfer the data in a bulk kind of fashion, instead of by character by character. What are character device? What are block device? The hard drive, the graphic card, they are block device, because you transmit the whole thing in terms of streaming or large amount of data. Okay, so therefore it makes sense that you have buffer cache, because of your device may be slower than the operating system. Okay, and then let's say the file system has to interface to memory system, okay, interface to whatever process system or CPU system, okay. So therefore the memory is much faster than those devices like the hard drive. So therefore having buffer cache, it will enable, the slowness of some device, so that it will not hold up the faster device or faster subsystem. Okay. um, I think as I told you, maybe some of you guys who are in my 222, I have shown you, let's say for in Linux. Let me just quickly show you. Um, in fact, when I talk about this block device or character device, if you do ls-l/dev and then type 2 more, You probably remember this command, right? This command, I'm listing in the long format, okay? And then I'm list a directory called slash def, which I know that all device driver, okay, associate with different devices here, okay, maintain in this directory, okay, because whenever you install the new hardware, or you have a set of standard hardware that operating system will support, but then let's say that you develop your own device and you install the new one. First, I mean, if you develop in Linux type of environment, you have to identify whether it's character device or block device, okay? If it's character device, then there are certain way to handle, because character device normally the way you handle those devices come with a sequence of character, right? Instead of a block of data, like in the hard drive, you're not sending byte because you sending byte, it takes forever. So a lot of time you send the whole block. So therefore it's separate, the device driver, which is a small little system software, okay, that will interface or interact with this hardware or hardware control. Okay, so in this case, as I told you, there's a character device or block device. If I say ls dash l slash def and then pipe to more, what does it mean by that? I think some of you guys probably know, because I know that there are gonna be hundred of files there. If I don't put pipe more, it's gonna show me just the last page, okay? But then when I do pipe more, it will show me page by page. So when I hit enter, now you can see that it show me the first page. It has, I think this one certain file system, the audio pipe, auto file system. Now, if you notice that the first column here, okay, when you see C here, these are character device, okay, and then the next 9 bits here, as you know, is the permission to a file, okay. Now let me just scroll to the next page, and I want to distinguish and show you the differences between character and block device. Now if you notice that, okay, here um, you have this number. Normally, regular file, you have file size here. But this device driver, instead of file size, because this is a special file that associated with a particular device, okay? The first column, this number, is represent a major number. Major number representing the device type, okay? Meaning that, let's say if you have a hard drive, the same hard drive, okay, from same company or the same type of file system, then you would have the same major number here. For example, BFS here, I'm not sure whatever this device, okay, but this device type is 23 here. And then it got 4 instance or 4 copy. Device type 23, device number 1, device number 2, 3, 4, 5, 0, 1, 2, 4, which means 5 instance of the same device type 23. And there are character device here. So that's what I'm trying to kind of demonstrate or show you. Let me try to enlarge. If you guys don't see it well, okay, you should type and tell me. All right, let me just kind of enlarge so that you see it a little better here. Okay, now let me scroll to the next one. Now you can see that instead of C, now you see B here. All right, the B, and then if you take a look, you can guess, because some of these are just the device name, and now I can guess that disk 0, this 0 S1, this 0 S2, this one S1, this one S2. These are a disk or hard drive, okay, which is the same type of I think because it plug into the same controller. In fact, right now, I mean, even though you bought Seagate or Toshiba or Western Digital, but still plug in into the same controller, okay? So the controller control the hard drive, and the hard drive, in fact, when you plug in using whatever those serial or the port, those are standard port. So the way, the controller speak to the disk drive, okay, is more controlled by the controller. So therefore, all these disk, okay, this 0 to this 1 here, they're all the same type 1, okay, and then it got totally 8 instances there. Okay, and then it indicates that this is blocked device. All right, guys. So I think this is just a short whatever demonstration showing you the file system and device. So in fact, the whole file system here is managed both device management as well as file management as well. And then underneath it, if that device become storage or file, then you have file system on the top here. Okay. So why don't we do this? Let me pause today's lecture because right now we are approached at the end of the period. Here is 9:50 right now. When we come back next time, I'll try to complete this file management of file system implementation, and then wrap up the lecture for this quarter. And then we're gonna start your term paper presentation next Thursday until we complete. And then if we have time left, I still have a few bonus materials such as virtualization as well as device driver or kernel programming. Okay, um, but you guys have any question, and feel free to type on this chat room. Otherwise, Carrick, I will go ahead and check the email, and then we can discuss more on this. Make sure you guys submit the dining philosopher this Friday. If you have any question, I'm now really pleased, happy that a few of you guys contact me, and I think last time, including Sunday, I have spoken to some of you guys, explain whatever you guys question. So if you guys have any question, feel free to contact me. Just give me the lead time 2 or 3 hours. I mean, appointment me 2 or 3 hours or one day ahead of time, and then we can get on the Zoom discussion and talk. Okay. Otherwise, still stay safe. Have a great weekend. Make sure that you do the quiz by Sunday midnight, and then we'll talk again on next Tuesday. Okay. And next Tuesday you're gonna see the list of your order, the presentation kind of order there. I still see that out of 36, still 4 people has not submit your presentation. Okay. Do it as quick as possible. Okay. And also for you guys, to when you guys start do presentation, please practice. If you want to add, change, delete something in your content, feel free to do so. I think the main thing is that I want you to teach the whole class with what you study there, and I'm excited to see and listen to you. So I think next class we're gonna do this YouTube live, and then next Thursday I'm gonna provide you the link, so then we can do the Zoom presentation. All right, guys. So stay safe, have a good weekend, and we'll see you next week. Bye.